let me introduce to you then Dan Tauriello. I'm sure most of you already know. Dan joined us here as an IT technician when he was working on your first degree, right?
Yeah.
Which was in biology, marine biologies. And then at some point after that, qualified to be out on the boat with Matt there, working on the relief captain and first mate, qualifications sorted out for that. And then came to me and said, I want to do some more studying. Can I do a master's program? Sure. Yeah, no problem. Have I got a problem for you? This is how we started down this path that he's going to talk to you about here as well. Well, with no further ado, Dan, welcome to your presentation.
Thanks, Brian. Thank you all for being here today. It's nice to see so many familiar faces. So my thesis was titled Advancing a Design for Trusted Community Bathymetry. And I'm going to start off by talking you into a reminder of the Trusted Community Bathymetry context, and then go into the ways that I went ahead and advanced that design. So a little background here. Despite rapid advances in technology that many of us work very hard to accomplish, mapping the seafloor at high resolution is an extremely time and resource intensive process. Here we see bathy globes showing some of the multi-beam coverage compiled, sort of centered on the Atlantic Ocean. And while we see that there is a significant amount of coverage here, there are lots of gaps to be filled. The latest JEPCO estimate of global seafloor coverage is about 23.5%. But keep in mind that number includes single beam soundings. So we all know many reasons we need high resolution bathymetry. These data sets sort of act as the base data to inform other development we want to do in the ocean environment. The reality is that hydrographic offices often lack, are we good? Are we still live? Okay. Hydrographic offices often lack the resources to comprehensively survey their authorized survey areas. And they need to use those limited resources toward prioritized survey zones. Those include dynamic areas or areas with commercial importance, or et cetera. To draw attention to that, the source diagram is a little blurry on the projector image here, but here we're seeing the Merrimack River. This is a very dynamic area that Matt and I transit every year to bring the boat to the yard. And oftentimes the buoys are not in fact placed where the chart defines them. We see the source diagram for this area defines that this area has not been mapped since 1969 when a partial seafloor coverage survey was done. So how can we go ahead and fill in all of these gaps? Technological innovation is something we all work towards here, and uncrewed, we're good? Okay. Uncrewed and autonomous vessels obviously provide an opportunity to act as a force multiplier. But the reality is that there are many more vessels that are non-hydrographic and carry echosounders capable of measuring single point depth values below their keel. Here's a nice gathering of non-hydrographic vessels accompanying a tall ship into Portsmouth Harbor last year. My next sliding for me, Chris.
Yep.
So when we gather data from non-hydrographic vessels of opportunity, by just collecting whatever data is available from the echosounder that happens to be installed on their marine network. We call this data volunteer geographic information. Private companies have provided many mechanisms to gather volunteer geographic information over the years. They normally provide a mechanism to log that data directly to their chart plotter, or to log the data from your marine network onto a datalogger device, which plugs into the network like that one. So what you're rewarded with a VGI data set like this is often the single point values, single beam soundings get interpolated into a digital terrain model like the one you see here. The issue with this is that it's a pretty picture, but oftentimes there isn't metadata or quantified uncertainty associated with those soundings. And so while hydrographic agencies retain legal liability for the depths portrayed on the chart, it's understandable that they're reticent to incorporate volunteer geographic information directly into their data products. Another thing that is not accounted for that's a substantial issue with VGI data is the oftentimes substantial vertical offset between the GNSS antenna and the transducer, which can be very significant on large vessels and can be a very significant error source in vertical uncertainty, especially in shallow water surveys. So one way of dealing with the uncertainty associated with VGI is to collect crowdsourced bathymetry. The idea behind crowdsourcing is that if we aggregate enough measurements of the depth at a single position, that the errors in sensor calibration, lever arm, sound speed, all of the things that affect the uncertainty associated with our data may cancel out, and then the resultant measurement of the depth that's aggregated at that point can be considered the correct one. The IHO defines crowdsourced bathymetry as the collection and sharing of depth measurements from vessels using standard navigation instruments while engaged in routine maritime operations. So the IHO began accepting crowdsourced bathymetry into their the Data Center for Digital Bathymetry database, where they're compiling global seafloor coverage. Here we see the CSV data that is compiled for the Gulf of Maine. And while we notice that there is some data density shown here, especially in areas where vessel traffic is naturally constricted by narrow waterways or by commercial shipping lanes, these constricted areas potentially can allow the opportunity for demonstrating a crowdsourcing approach to reducing uncertainty associated with VGI data. And folks over at the Canadian Hydrographic Service are actually establishing a calibration site in one of these constrictions in the, the St. Lawrence Seaway. And so we'll look forward to seeing how that works out. But the main takeaway here is that while there's some data density, these are uncalibrated soundings. And the reality here that we see is that for most of the ocean, a crowd simply does not exist. So bringing in the idea of trusted community bathymetry. So instead of dealing with the issues that I've discussed with VGI soundings or crowdsourced soundings, what if we instead produced a system that could collect single beam data from whatever echosounder is installed on your vessel, but collect it in a way that we can provide sufficient guarantees that the data can be used directly for hydrographic purposes. We can quantify the uncertainties associated with the soundings and provide the metadata necessary to use the data directly from this system for some level of hydrography. So a system for doing just this was presented in a Marine Geodesy paper in 2020. Here is the little datalogger enclosure. It takes up no more space on your boat than a pair of sunglasses. And the system demonstrates a ability to collect precisely geo-referenced soundings from any echosounder installed. It's capable of autonomously determining that offset I discussed between the antenna and the transducer with respect to the waterline. And it's capable of providing guarantees of data quality to allow the soundings to be considered directly for hydrographic use. Taking a look inside that box, there's a GNSS receiver board provided by CID. There's a custom input board to provide very low latency inputs for the navigation electronics. And then the brains is an Odroid C2 embedded single board computer. The system was navigated in the original paper by Novotel GPS 702GG survey grade antenna, and this comprised total system cost of about $2,000. So the work that I did was to advance this design in 3 ways. So I recognized that $2,000 is a very low cost for a generally survey grade system. What we can propose here is what if we could use a much less expensive antenna and collect observations that can be post-processed to produce position uncertainties on the same order as the uncertainties we gathered with the survey grade Novotel antenna. I also added a sidescan capability. So this brings in the opportunity to not only gather single beam soundings, but now we can generate an image of a target or a hazard, which provides a sort of unprecedented level of data richness to this TCB environment. And finally, I present an operational model in which a hydrographic agency could simply upload a series of waypoints to a TCB-equipped vessel, and the TCB-equipped vessel could go ahead and collect side-scan imagery autonomously as they go about their normal work. So the low-cost antenna that was chosen was the Harkson GPS 500. It didn't have any sort of special characteristics. There are competitors to this, but the characteristic that's important is that it provides a substantial price savings. Almost half the total cost of the TCB system is represented here. So in order to evaluate the performance of this antenna, I mounted it on the roof at CCOM. We actually have antenna mounts up there, for those of you who don't know that. And what I did was I logged GNSS data continuously for 10 days to evaluate the performance of the antenna and receiver combination throughout cyclic variations in the ionosphere. We converted those 10 days of observations to RINEX format and went ahead and divided up the data set into 24-hour subsets associated with each day of data collection. And I used 2 post-processing software solutions to generate single point position solutions for the antenna position for each day of observation. And I use those positions to calculate the baseline distance to a local NOAA CORS station, which is NHUN. You can see here with the baseline drawn between Chase and that control point. So here's a sneak peek at RTKlib. RTKlib is an open source post-processing software for GNSS positioning, which allows us to better estimate the errors associated with the observations. These include the satellite error, the tropospheric and ionospheric delays, and the clock errors. So you can simply provide your RINEX file, import those error models, and then RTKlib will provide you with a single point estimate of the antenna position for your observation period. So I meant to mention, in the context of this work, RTKlib is also going to provide a post-process kinematic record of the TCB system trajectory during data collection when we're going out and getting side scan. Opus is another post-processing software. It's hosted by NGS online. It simply allows you to upload a RINEX file, and then it draws in those error models that I mentioned in the last slide, and provides you with a single point solution for the antenna position, as well as the baseline distance to 3 CORS stations. And so here we can see the baseline defined in the output data file to NHUN. Results. Here's the geographic distribution of post-process solutions for the antenna observations during a 24-hour period. So each of these observations are taken at 1 hertz. We can see that the distribution of the observations is very tight. The grid lines here are only spaced at 2 millimeters. And so the solutions are distributed very tightly throughout the 24-hour period, and we're only seeing about 3 centimeters of uncertainty on each axis. If we go ahead and take those single point solutions from each of the 10 days, extract the mean position so they're rendered more easily to read, we can see that here each of the single point solutions rendered in 3D and then in cross sections. What we see here is that the daily estimates are very tightly clustered. The observations are very consistent throughout the 10 days, and we're only seeing about ½ centimeter of uncertainty in the declared position throughout the experiment's 10-day period. Here are the daily peak-to-peak errors provided by Opus. So this is the alternative to RTK-lib, essentially, for deriving the single-point solutions for the antenna position. And what we see here is that the magnitude of the errors reported by Opus is in good agreement with RTK-lib. We're seeing peak-to-peak errors on the order of 1 to 5 centimeters throughout the experiment's duration. I went ahead and calculated the baseline vectors from each daily single point solution for the antenna position to the NOAA core station, NHUN, in order to evaluate the precision of the position solutions. They were in very good agreement. The peak discrepancy throughout the 10-day period was about 4 centimeters. So in conclusion, this Hartson antenna provides a really good low-cost solution that allows us to collect observations which can be post-processed to produce solutions with the same uncertainties as those we see with a survey-grade antenna that is much more expensive. The peak-to-peak errors in the vertical were less than 5 centimeters and less than 3 centimeters in the horizontal. And this was with kinematic position corrections applied using rapid ephemeris. If we had waited the 2 weeks for the precise ephemeris to be published, we may be able to reduce these errors even further. There was very good agreement in the results derived from RTK-lib and Opus in both the peak-to-peak errors we saw throughout the experiment and the baseline calculations to the known control point, NHUN. So the second major component of this work was integrating a Garmin sidescan module with the TCB system. Sidescan, like I mentioned before, acts as an incredible force multiplier in the TCB context. Instead of collecting single point values, we are now generating imagery of the seafloor, of the water column. We're getting textural details of the geology, etc. Most importantly, in this context, I think sidescan integration allows the opportunity for a TCB vessel to verify the presence of a hazard without requiring the vessel to pass directly over the top of a potential hazard. So this module wasn't chosen for any defining characteristics. Its spec sheet is similar to its competitors on the market at the time. It is single beam and side scan capable. It is capable of producing 2 chirp pulses at high frequencies. It's got a temperature sensor integrated. It's got about a 1 degree beam width in its side scan mode. And most importantly, it's only $500 with the transducer included. So if you take a look, this is the processor enclosure for the system. And on the front of that, there's a 3-port Ethernet hub. That's because modern sounders generally communicate using an Ethernet protocol that's proprietary to the manufacturer. When we began this work, I did a fairly exhaustive literature search to try to find a commercially available unit with a published network protocol. It saved me a lot of sleepless nights, but unfortunately that was not available. So I'm going to start talking about how I went ahead and reverse engineered the network protocol associated with this system. So here is a generic installation schematic. It's fairly simple. The transducer gets plugged into the processor with the cable they provide, and then up to 3 multifunction displays can be connected with just regular Ethernet cables to the processor enclosure. And you provide DC power and you're up and running. So the way I started reverse engineering this thing was to place a passive Ethernet tap between the processor and the chart plotter. This allowed me to monitor the network traffic moving in a single direction at a time via one of the receive-only ports on that tap. What you're rewarded with when you tap into this little tiny network is something like this. This is not rendered very nicely on the projector, but it's an image of Wireshark, which is just an open source network software. And what you see in Wireshark is that there are lots of conversations going on. There's 14 or 15 multicast conversations. There's a whole bunch of TCP/IP connections, etc. So what I did to start narrowing down the conversations and the data that I cared about was I did silly things at my desk. Like I put the transducer in a bucket and I applied sounder settings back and forth. And then I monitored the network packets and tried to figure out which had the strings that I needed. And then I tried to produce really unique images on the chart plotter screen in hopes that I could reassemble the image in a way that was coherent and I could recreate what I'm seeing here. So what I found is that there are 2 connections that are important in the context of this work. There is the sonar control data stream, which is a TCP/IP connection, and there's a sonar image data stream, which is a multicast data stream. So let's talk more about those. The control data stream, I figured this out by, once again, toggling sounder settings right in the bucket. And then eventually I was able to narrow down the packets containing the actual command string, extract the header data, and then finally extract the actual string with the command. Here's a little snippet of one of them. And what I was able to do is package those commands in some Python code that allowed me to build my own network packet and then distribute that command from a computer of my choice. So now we're headlessly controlling the side scan. The image data stream was a bit more complicated. This is the multicast data stream. The basic structure consists of an Ethernet header, a data header, and then there are 3 ways that the system provides visualizations of the side scan record. And each of those data blocks are preceded by their own variable length header. The way that this works is that a single scan line is composed of 14 consecutive UDP datagrams, and they come in sequential groups of 7. Which are associated to either the port or starboard stave. So now when we really get into the fun part, here is the image data stream filtered out in Wireshark. And so if I extract the Ethernet header data, convert the hexadecimal values to 8-bit unsigned integers, and then render all of that as pixel values, I wind up with an image like this. And here's our first look at the 3 data visualizations. This is Viz1, Viz2, and Viz3. So when we parse all of this correctly and reconstruct it, here's what we were rewarded with. Viz1, Viz2, and Viz3, of course, from a single stave in these images. So Viz1 is likely the raw digitized side scan imagery because we see a very small range in the small dynamic range in the pixel values shown here and from the histogram. Viz2 and Viz3 are both 2-byte average versions of Viz1. So the total swath width of Viz1 would produce an 8,000 pixel swath. Viz2 and Viz3 are both 4,000 pixel swaths. Viz2 is dynamic range adjusted to emphasize what seemed like the highest impedance contrast in the image. And then Viz3 is a 2-byte average version of Viz1, which produces a really nice high contrast image. And this is the visualization format that the chart plotter actually uses to display the data. And so I'll go ahead and use the Viz3 rendering as the demonstrator for the rest of the work here. So here's what you get when you reassemble the Viz3 format using some custom MATLAB code. And there's the full swath reassembled. So now that we can rebuild the imagery from the data stream, we need to be able to convert it into some format that we can manipulate using the softwares that we like to use. So I went ahead and wrote a custom adaptation of a Python library that goes ahead and produces an XTF file that you can import into HiPAC or SonarWiz or your software of choice. When we write the XTF file, the navigation record is interpolated with the sidescan imagery, and then the appropriate metadata for the sidescan record is baked into the file, and you are rewarded with an XTF file like this one. Here's the raw chart plotter photo, and then here's the XTF file imaged in HiPAC. So now the idea is to be able to do all of this using the TCP data logger directly. So the goal here is to use the logger to now control the side scan. So we no longer need this device, and then to log the imagery from the data stream directly on the logger, and then to use that data to produce a precisely geo-referenced text file or a XTF file with some account for latency in that data set. To control the sonar is fairly trivial. Like I mentioned before, I was able to install Python on that little Odroid computer inside the data logger. And then I could build a library of Python scripts that allowed me to send datagrams with the command strings for the sonar controls. In order to log the side scan imagery using the data logger, we are, of course, resource limited since we're using very small form factor electronics. So I used a utility called dumpcap, which is a command line based network capture utility that allows us to filter network traffic in real time, and it supports nanosecond precision timestamping for those data packets. And you can see here when we are logging side scan data at the highest possible rate the system is capable of collecting it at. We're consuming less than 1% of the system's CPU and 10% of the memory. So it's a very efficient process. We're all familiar with the idea that if we ignore latency in hydrography, we end up with a systematic positioning error, which magnitude grows with vessel speed. For example, here, if latency is properly accounted for, we get nice co-registered bathymetry regardless of vessel speed. And then if we are improperly accounting for that latency, we wind up with some type of offset like that. So what I did here was an experiment to attempt to quantify the total system latency associated with the digitization of the side scan records. So the time in which the transducer receives the incoming echo to the time that the digital side scan record is time-stamped in the image data stream. The way that I did this, unfortunately, Val couldn't be here, but he gave me some lunchroom ideas that helped me figure this out. So I appreciated that. But the way I did this was on my kitchen table, and here are the data logger. This is a different form factor, but the same components of the data logger. And here its guts spilled out on the kitchen table. This is the embedded Odroid computer. And what I did was I used a tap of my finger on the transducer face as an analog to an incoming acoustic pulse. So how this worked was when I tapped the transducer face, I simultaneously connect these two wires. This closes a pull-up resistor circuit and triggers a system interrupt with an associated time tag. It also, my finger presents a nice impedance contrast in the side scan record, and I can then extract the timestamp associated with the first datagram in that side scan record. So I went ahead and did that many, many times with the side scan configured to be at a variety of range settings to see if there was any difference in latency with side scan changes in side scan range. I found that there really was not a significant difference here. So here is the combined probability density function of the data latency at all range settings. We can see that the function is reasonably approximated by a gamma distribution, and that the mode of the distribution is about 0.24 seconds. So I use that 0.24 seconds value as my latency correction for the rest of the work here. So to see if I was right, we went out and did the latency patch test. Two locations. Here are sites A and B, right on the Piscataqua River here. Site A, I imaged the chain for NOAA buoy, navigational buoy GC3. This was collected at 800 kilohertz with a 40-meter swath width. Here are the resulting records. So this is the chain at 4 knots and the chain at 8 knots. And I wanted to take a quick detour to take a look at the PPK record from the trajectory during this data collection. We see here is that the data is very good. It's completely dominated by fixed ambiguity solutions. There's only a few floating point solutions in yellow that you can see in the data set here. The vertical uncertainty reported by RTKlib was less than 1 centimeter. In the horizontal uncertainty was less than 5 centimeters, which was a little bit surprising since we'd expect the horizontal uncertainty to be less than the vertical uncertainty. But in the context of this work, these uncertainties are very small in magnitude compared to the uncertainties associated with the side scan data. And so it's probably not a significant issue here. So when we look at the side scan record, the mooring chain was nicely co-registered in both data sets at 4 and 8 knots, and we're seeing about 30 centimeters of horizontal uncertainty, but almost all of that uncertainty is in the across track direction, and so it's probably not really related to a latency issue, and it's probably more related to just the vessel crabbing differently with different speeds in this area. So I did this again with a target found by the state pier. And here are the resulting side scan records. Once again, we get the position of this target nicely co-registered in the record with horizontal uncertainty on the order of 80 centimeters here. However, almost all of that is once again comprised in the across track direction. And here's a little peek at probably what's going on here to cause that error. Here's the state pier. We see at 4 knots, the vessel heading is probably nicely aligned to the state pier. And then at 8 knots, the current is forcing us to turn and crab away from the pier. And so we're seeing this offset between the satellite imagery and then the pilings of the pier here, which is indicative of probably why we're seeing that crabbing artifact in the data. So to review, now we can control the sonar and log the side scan imagery using the TCB data logger. We can compensate for the system latency, or at least the digitization latency associated with it. And we can produce a geo-referenced XDF file that can be dealt with like all other side scan data in a hydrographic software of your choice. So what about the final requirement, which is autonomous operation? We can't leave the burden of controlling this thing on the volunteer vessel. So I want to present a concept for operations and then demonstrate that concept in which a TCB vessel may carry a series of waypoints. Okay, don't hit the wrong button. So concept of operations, which TCB vessel may carry a series of waypoints for a hydrographic target of interest, autonomously detect when that vessel is within range of one of these targets, and then turn on the side scan, apply appropriate settings to collect the data, log that data, and then render it as an XDF file. So here's a quick installation topology on how we did this. We see the antenna installed with a nice clear sky view on the Gulf Surveyor. We see the transducer looking feeble on the bottom of our instrument deployment strut. Here's a chart plotter with, a multifunction display from Garmin, which is just providing us a real-time display of the side scan data. Here's a form factor of the TCB data logger and a DC power supply. Okay, so here we see the output of a real-time file that is generated by the GNSS receiver. This is a text file, and it reports the position of the antenna phase center in ECF coordinates, which you can see here. It updates this position at 1 Hertz. So what I did was I wrote some Python code which monitors the position reported here and then compares that position to a list of waypoints for areas of hydrographic interest. And so now we can detect when we are within range of one of these waypoints by generating an imaginary boundary circle. So I drew the imaginary boundary circle for purposes of the presentation here, but the idea is that around each of these potential targets of interest, a boundary circle gets automatically generated with a radius that is appropriately scaled to allow us to image that target with the given the water depth and the range we expect the side scan to be able to use in that water depth. So in deep water, the radius of the circle is closer to 3 times water depth, and shallow water is closer to 5. So now as the boat enters the circle, we detect that we're within range of imaging a target. We apply settings, we log the data, and then as we exit the circle, we automatically secure the sounder and wait to detect the next location. Here are the results of some of these automated scans. So here's a boundary circle generated by the UNH pier. As the Gulf Surveyor transits through that boundary circle, we collect the side scan record here. And then here's an XDF file overlaid on some satellite imagery of the pier with the water column removed. What we can see is the system's capable of collecting really impressive imagery. Here are the pilings for the bridge, for the pier structure. And then here we're actually seeing 4-inch PVC pipes, which act as the seawater intakes for the Coastal Marine Lab. As well as great other textural details in geology, etc. Here's another automated scan of the Schiller Station Pier. I left out the boundary circle just so you could see how nicely the side scan data co-registers with the satellite imagery here. We are seeing some of that heading artifact show up here after we had turned the corner. There was a very strong tide at the time of this data collection. And here's a closer look at that data set. Here are the pier structures, very nicely imaged, and we're seeing really nice textural detail in the bathymetry as well. So what we really want to do is be able to define several targets, or a list of targets, and have a TCB vessel autonomously detect when it's within range of those targets as they're traveling around in their normal operations. And this would allow, this would provide a TCB equipped vessel with the opportunity to see where these areas of hydrographic interest are directly on their chart plotter display. So this is Rose Point Coastal Explorer, which is the chart plotter we use on the Gulf Surveyor. And it would allow the vessel operator to go around and to potentially image exciting targets, which everyone likes to do, to collect and contribute to the TCB initiative, which benefits the Hydrographic Agency. And it also accumulates a data set of interesting imagery with this sounder that the sounder manufacturer could use to try to incentivize unit sales. And so here's a short demonstration of this concept. Here's the resulting imagery as we traveled around on the Gulf Surveyor. And here's some closer looks at that imagery. Here's 800 kilohertz scan with a 40-meter swath, and these grid lines are spaced at 1 meter. And I just wanted to show you the details that we're seeing here. This is probably a surface marker line for the string of lobster pots. We're seeing lobster pots here, here, here. So this is probably a piece of 3/8 pot warp that we're imaging. And then we're seeing really nice textural details in the geology, et cetera, here. One other image I wanted to share is a record gathered underneath the Memorial Bridge in Portsmouth. I thought this was impressive for a couple reasons, in that it was impressive that the navigation record wasn't corrupted by the multipath effects of the bridge. We also see really nice sand waves details here. We see the main piling structures for the bridge on either side of the main span, and then we even see scour around those pilings. So hydrographic agencies have been integrating data of unknown quality into the chart for years, such as the data that might be derived by targets detected by a TCB sidescan system. I just wanted to mention this quickly, that there are classifications for soundings to reflect the uncertainties associated with them. And these are a number of symbols that could reflect that, approximate positions or approximate depths, etc. So while the side scan capable TCB system is pretty impressive in what it is able to do for about $1,000 that we're talking about here, we recognize that $1,000 still may be a price that's prohibitive to widespread adoption. What we want to do is use these systems to make a serious dent in global seafloor coverage. So consider the idea that we use a TCB system as an authoritative system to cross-calibrate the data collected by VGI systems. So here is a bathymetric data logger, which simply logs the data available from whatever sounder is installed on your marine network. What's unique about this is it was developed in-house here, and it is cheap. It could be had for about $10. So consider the idea that we distribute hundreds or thousands of Wibble loggers onto non-hydrographic vessels in a geographic area, and then use a TCB system to go ahead and cross-calibrate those soundings. And this idea is being investigated by collaborators at USF to go ahead and demonstrate cross-calibration. So in conclusion, this work demonstrated that it's possible to use a cheap antenna to collect observations that can be post-processed to produce a position record with similar uncertainties to those collected with a more expensive traditional survey antenna. We demonstrated that we can make TCB data far more valuable by integrating a side scan component and providing the opportunity to generate images of targets on the seafloor instead of only collecting single beam soundings. And we demonstrate an operational model in which a hydrographic agency could upload a series of waypoints to a TCB data logger, and then the data logger may go and collect side scan imagery autonomously without any input from the vessel operator. So I appreciate all of the support here, and I really look forward to seeing how the TCB project and idea progresses over the next years. There's a lot of interesting research that's still being done here, so I hope this thesis inspires interest from recreational sonar manufacturers, from hydrographic agencies, and from students and researchers who may continue to develop this idea. Thank you.
Thank you, Dan. It's good.
Thanks.
Questions? Patrick.
I may have missed it. If I did, I apologize. You're talking about radii around objects of interest or whatever bounding boxes being placed in like Coastal Explorer, for example. Yeah. Who provides those, or who could provide those in the future? In the U.S., are we expecting NOAA to produce these and somehow blast them out to the outside world, or is there some other avenue for that?
Yeah. So the boundary circles could remain imaginary, and so there's sort of two concepts here. A hydrographic office may upload a series of waypoints for targets of interest, and then a TCB equipped vessel may simply detect when they're within range and go ahead and collect that imagery. And the vessel operator may have no idea any of that is going on. Alternatively, what I talked about was having an integration from companies that produce these chart plotters, such as Rose Point or Garmin, et cetera, and having them actually display some sort of TCB extension on their chart plotter, which could generate something like a boundary circle that would allow them to define, hey, there's something interesting here, maybe I should hit that as I pass through. So I think in this concept, the hydrographic agency would sort of define what the boundary circle is. But you know, it could be implemented in a variety of ways.
So related question.
Yeah.
You're saying the hydrographic office could do it. You know, it doesn't have to be the hydrographic. It could be anybody.
It does not. No.
But ideally, it would be somebody who had interest in the data. Correct?
Yes. Yep. Yeah.
And if I could just follow up right on that. Is it a data volume issue? Why don't you just, if it's all happening magically behind the scenes, why don't you just collect it all the time? And
yeah,
it's not, yeah, there may be an area, but it's all the areas we don't know about.
Yep.
I'm probably even more concerned.
Yeah. It will have to depend on the vessel's opportunity to offload data. So some vessels have internet connections and offloading data is trivial. Some vessels are rarely within reach of the outside world. So I did some work I didn't include here, but I looked at the data volumes generated by the sounder, and I found that I could log, I think it was about 20 hours of data at the highest rate the sounder was capable of collecting it at with a 15 gigabyte SD card. So it's sort of a question of how much money do you want to spend on
the side scan or
yeah, the side scan. So the logger, it generates a couple megabytes of data per minute, basically. So it kind of depends how much money you want to spend on data storage and how fast you can offload it. Yeah.
There's also a question of having to scan all that data as well, which, you know, the standard problem says. So,
have you been to something like an NMEA conference or something like that?
Haven't.
So, do you have any feeling for what the reaction is to this work from the likes of Garmin?
I do not have a feeling from the likes of Garmin. There has been interest from sonar manufacturers who have just sort of interacted with in our daily work on the boat here. And it seems to be positive. So I haven't presented this at a conference though.
I don't know if you remember, I certainly remember, we did visit Klein.
Yeah.
And they were, I mean, I don't think they were worried, but they certainly were concerned.
Yeah.
One of the Peter Huntsman, said to me, we have to make these new systems because some idiots keep making $500 systems that are just as useful.
I think presenting this at the conference was definitely generates some.
Well, I had another question that I wasn't going to raise here, but I think I have to now. And we've had little discussions about this. How legal is this? You didn't break it. You didn't break a seal.
No.
You really were just capturing, and that was our rationale. You really were just capturing data that was freely being sent over a port.
Yep.
But
there was no data protection scheme or anything detected.
So I promised Dan I'd field this one if it came up. this is my idea, so it's my fault. So there's two aspects to this. One of the reasons why we started with the Garmin system is because I actually know how it works. I'm just not allowed to tell you because I found out how it works under an NDA for various reasons. So I had no part in the reverse engineering because I'm not allowed to. Dan did it all himself, which you should be impressed by. There's nothing illegal in the reverse engineering. We haven't released any of this software either, nor do we intend to. The point to demonstrate here is the capability of these side scans, because none of the manufacturers would play ball and let us know how to do it. We had to do it ourselves. Ideally, what would happen is the manufacturers would do this and either publish a network protocol or build it into their own system so that we don't have to. So the core component here is not really the reverse engineering. That's an impressive Deadpool feed in itself. The core component here is an interoperability with a small recreation side scan. So that's really the bit that we should focus on here. The reverse engineering is a necessary concomitant of what we demonstrate.
And I'm just thinking, so if Dan gets up at a meeting.
Yeah, we'd have to be careful how we approach that. And it was one of the, actually, we talked to, or Dan talked to Unich Innovation. Unich Innovation declined to license it even because they were concerned about exactly the same aspect of it. And so I think the value here is the demonstration that we can do it. If we were going to do a commercial version of this, we would have to talk much more deeply with the manufacturers if they were even interested. Fortunately, my experience with Garmin particularly is they have said in multiple cases that they're interested in nothing other than batteries. Use the batteries, nothing other than.
That's kind of why I asked the question, because behind closed doors, and if nobody hears about it, they'll probably be feeling safer. But if this gets presented at a larger venue with a big audience,
that's one of the reasons why it hasn't been yet. Yeah. Okay. Further questions? So at least one more. Andy, please.
So, if I'm at the hydrographic office, what's the way forward for me to, and this probably involves several pieces of the process. What's the way forward for me to make use of this? I mean, somebody's going to send me this big stream of Garmin side scan data that I'm going to scan, or am I going to have to send everybody in the power squadrons a list of contacts to search? So how do you see this unfolding in a useful way? It's kind of a scenario.
Yeah. This isn't a production system, just to be clear. But
No,
if it were, I think the idea would be that the onus on the hydrographic office would just be to provide coordinates for locations that they're interested in getting side scan imagery at. So this could just be a list of coordinates. And then on the back end, after the data is autonomously collected, there would have to be some data offload mechanism, which we didn't really discuss. And the data can be rendered in XTF file format. So it can be dealt with just like any other side scan data set that the hydrographers are already used to dealing with. So it should be fairly, trivial to deal with the final product after the data has been processed into that XDF file.
I would contend that the answer is the next thesis, which is going to automatically extract targets and just send the targets to the hydrographic agency, and then you can run it all the time. But that would be really.
The other mechanism is that the IHO have developed a series of trusted nodes, which is not really part of this discussion, to handle volunteer data. And the idea is that a trusted node aggregates and deals with the data and then renders it in an appropriate manner. Currently, those nodes are looking at just single beam echosounder observations, although Far Sounder, who became a trusted node this year, want to render their forward-looking 3D data as well into the database, which I think freaks out DCDB just a little bit. Personally, I think that's probably the mechanism. There would be some mechanism like that. There's somebody who's going to sponsor this effort, either the hardware manufacturer or some third party. They're the buffer to the hydrographic agencies, to talk to the hydrographic agency and say, hey, we can render this data. How do you want it? What's useful for you, and make sure that contract is beneficial.
So let me follow up on Patrick's question too, which was one question that I posed to you on my remarks on your thesis earlier. How would let's say the hydrographic office issued this set of coordinates of interest, and then with them had a positioning uncertainty. I mean, when something is on a chart as position approximate, well, first of all, if it's on a chart accurately, probably don't need to know about it. So like a known thing is probably not of interest. But something that's there inaccurately is there because the person who sank in the boat or whatever said, well, I was about there when I sank, which, as you can imagine, might be pretty far off. So the hydrographic office might have an area of uncertainty. The AVOICE file, for example, has uncertainty circles. So how would if you had positions and uncertainty, would you see a mechanism to sort of preset your system for that?
Yeah. So I think if you have uncertainty, you can just take the farthest bounds of your uncertainty envelope, and you can say, I want to get the best chance. I want to take the best shot at imaging this somehow. And so if a vessel comes within one of the edges of this uncertainty envelope, I'll expand my boundary circle to include all of that. And if we come basically anywhere near this area of the uncertain target, we're going to turn on the sounder and go ahead and collect side scan. So that may not always provide the best imagery, but I've been sort of talking about this in the context of the boat is not out there to collect this data for us. They just happen to be passing by. And so I think that would be sort of how you could implement that, and just to increase your boundary circle range, essentially.
So to be clear, it doesn't have to be a circle, right? It
doesn't have to be a circle, no. Yeah.
Have you considered giving a user alert where somebody is just navigating, not planning to do anything, but alerting them, hey, there's this area that is of interest?
Yeah.
Do you have time?
Yeah, that was sort of what I was trying to get at with that chart plotter integration, where I showed Rose Point with some boundary circles. So we could have any symbol or any alert mechanism there. I just chose the circle as the demonstrator.
Yeah, but I mean more if they're not running Rose Point, but just giving them some kind of alert.
Yeah, that would probably be a mechanism that would need to be, worked on collaboratively with the chart plotter manufacturers, I suppose.
Yeah, Elise?
Nice job, Jan.
Thank you.
It was nice to see the low-cost antenna, the performance, that was impressive. But I just have, and I know you mentioned that you tested it around the bridge, to see the performance. Can you talk more about that? How the system performs when you use it around under the
Oh
bridge?
yeah, I showed the scan under the Memorial Bridge. Yeah, what I was getting at there was I was just impressed that the record wasn't impacted by multipath from the bridge because it's an enormous steel structure over us. That was not, that was more of the exception than the norm, to be honest. I got that one record and it was very good, and I was kind of surprised by it, and that's why I left it in there. But I did see multipath degradation in the records otherwise.
Yeah, because it looked like a magic to me, like
Yeah.
Well, to be fair, the survey grade antenna that we used for the initial experiment had exactly the same problem. So it even with a really good antenna. Brian, I think you had one still relevant. Want to ask it? You good? Okay. All right. Right.
So there was kind of two groups talked about. There's a crowdsourced bathymetry group and the trusted bathymetry group. And this is to go on the trusted group. What types of ships is that would be going on?
Well, look at me, look at him.
Sorry.
Yeah, so these are all systems that can be deployed on non-hydrographic vessels. Crowdsourced bathymetry data loggers or volunteer geographic information data loggers are sort of the same thing in this context, where we're just placing a data logger on the marine network and logging whatever depth data is available from whatever echosounder is installed on the boat. The idea of crowdsourcing is just, can we aggregate enough of that data to reduce the uncertainty to some level that we're happy with? A TCB system is installed on the same non-hydrographic boats, except instead of just simply logging the depth message from whatever echosounder is installed, we do that, but we couple that with a positioning system and a low latency data logging method to try to reduce the uncertainties and allow us to quantify the uncertainties associated with those soundings.
So that's where the trusted part comes in.
That's the trusted idea. Yeah.
Let me ask the question a slightly different way. If you were going to go into the harbour today, which I know you're going to do, and you're going to go, which one do I want to put a trusted logger on? What would you look for in a boat to put a trusted logger on?
Well, you would want a boat that's active, ideally, and a boat that, well, I mean, you would want a variety of vessels. It would be nice to have vessels that, there are lots of vessels that sort of travel the same route every day. So that could provide you with a nice calibration data set. If you look at all of those soundings over time. And there are other boats that go different places and can gather information on areas that are poorly charted, which is what we're trying to do. So I don't know, I would put it on a variety of vessels, I guess. I would try to pick the ones that have a, I would try to pick the ones that have a decent recreational echosounder installed in them, and ones that have that transducer installed in a way that it is likely to produce good data. And then I guess I would.
So what would cause it not to generate good data?
Oh, lots of things. People install non-rigid mounting systems for transducers, or they install them in places where they suffer from aeration from the vessel hull or the propellers, etc. Yeah, if their transducer was mounted closer to the center of gravity of the boat, that would be probably most ideal. Yeah.
So to kind of somewhat follow up on that question, you're proposing to extend Weeble by TCP or TCP by Weeble, however you want to word that. Would it not be worth to make the TCP slightly more expensive for the reason that it became clear from your delay analysis that the largest horizontal uncertainty comes from the heading?
Yeah.
Would it not be worth going for a 2 antenna configuration?
it could be worth doing that. If we're able to resolve a heading on the order that we're hoping to with a 2-antenna configuration, it would obviously make the system installation more involved in that they would have to set the antennas correctly and place everything very precisely, and then they would have to perform some sort of GAMS calibration. But I think that's a great idea. The other thing that we could do that may offer a little lower barrier to entry is to simply log whatever heading NEMA sentences are available on the boat's network. If they have a heading sensor that's providing that information, and we could probably integrate that heading to do some sort of correction as well. So.
Further questions?
Yeah, Dan, I think you teased that you've thought about some ways to offload or upload that data. You mind just touch on that a little bit?
Yeah. So the data sets are not particularly massive, although they could be if we upgraded the storage to some extent on the data logger. But the easiest way would be to use some method to connect the data logger to the internet. You could use a USB Wi-Fi dongle and plug it into the Odroid computer, and then do data upload directly like that. So that would be sort of trivial with a vessel like the Gulf Surveyor, where we have great internet connection. If you do not have an internet connection, it gets a little less flashy in that you are probably going to be carrying that data on a USB stick or something. And this is where those trusted nodes come in the IHO's model for gathering crowdsourced data, and that the trusted node, it acts as an organization or individual who is responsible for sort of dealing with that transfer of the data from the boat to the end user, the hydrographic agency, etc.
So do you know what is the reality in America about internet connection, a vessel? Like
The legality?
No, the reality, like
the reality.
is that available like quite often?
I would expect it, yeah. I would expect it's becoming more and more common. The availability of devices to connect you to the internet is phenomenal now, right? And they're becoming very cheap. What?
Elon Musk,
yes. Yeah, Starlink is offering a tremendous opportunity to connect to the internet from anywhere in the world. And so that'll probably transform, marine connectivity on boats and ships or some analog to that satellite derived data stream that comes along. So I don't know how many boats actually have an internet connection, but creating an internet connection is fairly trivial these days.
A lot of marinas have Wi-Fi.
Yeah. Yep. Yep.
As part of going over your points of interest, we can send a warning out. That was suggested at one point, but like, is there any implication on vessel speed? Because if these go on to recreational boaters or like sport fishing or something, they got their twin 250 horsepower motors going, 20 knots or something.
Yep.
Do we have an issue?
That's a good point. As someone who doesn't operate a speedboat, I don't think about that very much, but that's very true. So we could involve a mechanism for trying to get the boat driver to collect good imagery, so that that announcement could include something that says, this will best be imaged at 6 knots. So I think that's a good point. It would be cool to include some sort of guidance on how the imagery could be best collected, especially for those who really want to contribute in the best way possible.
Would you envision the speed being logged as part of the data set?
Yes, it will be logged via the navigation system already, so you should be able to extract that. Yeah.
Last questions, anybody?
There's one online. There's one online, yeah.
Oh.
Hi, Daniel. Thank you. Very nice work. So, very impressive presentation. I just have a few questions. Also, following up on the question someone already asked, in terms of the difference between what makes it trusted crowd bathymetry and what is just crowdsourced bathymetry. I would assume that for it to be trusted, I also heard discussion of if you have to mount it somewhere. Do you take care of the setting up of the logger or installation in the vessel on the vessel, and does it? I would assume that the metadata is available for the vessel, like in terms of where the antennas are mounted, the offsets and all that, compared to just crowdsourced bathymetry, where the major problem is that, or one of the major problems is that the metadata is missing. That's my first question. Like, is where does the metadata stand in this case? On the second hand is I tried to join the presentation at 5 exactly, 5 my time, but I couldn't get in. So I joined way later, and I think I missed some part of the presentation. So I wanted to know, like, is your thesis going to be available publicly? Is there somewhere one can access it if one is interested in this topic and wants to read further or get some more knowledge? Or likewise your presentation as well? Or it's something one has to contact you or CCOM privately?
So I'll take the second question. It was, hello, thank you for joining us. This is Brian. So we are recording this presentation, and typically, unless it's an objection, we make those available on our Vimeo channels. You'll be able to see it from there. As a matter of course, all theses that are developed and produced by the university are made available in a standard repository, and you can get it through interlibrary loans if you wanted to get that. We typically also make them available on our website, unless there's some reason not to, or at least through the university's scholars repository. So that should all be available to you. So the first question was about metadata and where we generate the metadata. Dan, take that one away.
Yeah, I will try to. It was a little tough to hear you there, but I'll try to address what I think you were asking about. So I think you started with the difference between CSB or crowdsourced bathymetry and then trusted community bathymetry. And then I think you were asking about how we generate the appropriate metadata to collect trusted community bathymetry. So to start, the difference between crowdsourced bathymetry and trusted community bathymetry is that crowdsourced bathymetry is just simply volunteer geographic information, and that we are just logging the single beam depth values provided by whatever sounder is installed on a volunteer vessel. That data has often no metadata associated with it, and is problematic for the reasons that I had discussed at the start of the presentation. The trusted community bathymetry system differs from a volunteer geographic information or a crowdsourced bathymetry system, in that it still goes ahead and logs whatever depth data is available on the vessel's network, but it captures that data using a data logger that has been specifically developed to do that in an efficient way and with as little latency as possible. And it pairs that with a GNSS antenna and receiver combination that is capable of navigating the system very precisely during data collection. The metadata I think that you're talking about associated with where the devices are installed on the vessel can be automatically resolved by the TCB system. And that is all detailed in the Marine Geodesy paper that came out in 2020. So that's why I didn't go into a lot of detail and how that works, but basically the system is capable of automatically determining the installation offset between the antenna and the transducer so that the vessel operator has no obligation to go ahead and measure those, and we do not risk errors in measurement. So does that answer your question?
You should also mention about the horizontal piece.
The horizontal piece.
Yeah, Casey's thesis.
Oh, right. I didn't mention here as well, but the horizontal uncertainty in the installation locations of the sensors can be resolved using a variety of methods that we've looked into. So there's a graduate student named Casey O'Hearn who did a thesis where he used drones to collect photogrammetry and LiDAR data sets as it flew grid search patterns over the top of a vessel. And then he was able to derive the horizontal offset estimates from those data sets from the drone. And he was able to constrain the horizontal uncertainty to within centimeters using some of those methods.
And there's also a paper on that published as well.
Yeah, his thesis is published. And
so I'm going to try and round this up now, unless there's some last minute pressing questions. Time is ticking on here. You okay in the room? I didn't see any others. There's one more question in the chat, which was about who provides funding to the volunteer vessels. I think that's probably outside the scope of Dan's thesis. So if you're interested in that, let me know. I can talk to you about that one, whoever that was on the connection. No more questions in the room? No? Well, please join me in thanking Dan again.